All right. All right, seems like it's taking a little while to get the computer going. I'll get that going in a minute. Let's take a look at the first part. And what we see here, oops, there we go. It says data table. What's going to happen is, certainly I was given data tables a lot, and they were done for me, and it makes it look neater and stuff like that. And I kind of like the idea that I had a place to put my numbers, but I don't think it helped me understand science very much. It told me, put your number in this box where I told you to do it, and yet I don't think it helped me understand science. Why is it that people sometimes don't understand the ACT? And I know this has been a weird year that with testing, stuff like that. That's very unusual. My whole life, I've never heard of this where they kind of don't give the test, or colleges are now even looking at people without any test scores at all. It's very, very unusual, I think. So going back to the ACT, why is it that the science part of the ACT, somebody said, well, you can't ever get ready for that. Well, you can. You actually can. And they're actually looking for things that maybe all sciences have in common. And so, for example, the skills that you learned, even with this graphing thing, that it's actually part of the ACT. I even printed out I'll show you one later, I printed out a couple pages of an old ACT, and of the 7 sections that they ask, most of the time, 5 of the 7 have some kind of quantitative data. It's going to be in the form of a table or a graph. And so what happens is that some people don't understand that it doesn't matter. They say, well, I've never had microbiology. Well, it's okay. It's okay you haven't had microbiology. All right, come on, crank it up. It's okay you haven't had microbiology. They're not asking that. It is true that if you have had chemistry and they ask a question about chemistry, you feel more comfortable with it. That's true. But you don't have to have had geology to answer a geology question on the ACT. This is weird. It's not the way it normally happens. What is it? Huh. Where is it? Yeah. Okay, there it is. There it is. All right. So what is it that they have in common? And so what I'm going to try to show you with this graphing thing is, if you did the experiment, what would your data table look like? And let's take a look at this right here. If this was your experiment and you had to graph it, which one would you put on the x-axis and which one would you put on the y-axis? And why? And what I'm here to teach you, I think, is that if I start having you do your own experiments, if you do your own data tables, and then you have to do your own graphs, you'll figure out what they mean when the ACT. If you look at someone else's experiment, you can almost picture yourself doing it. So I picture myself doing that and say, which one was the independent variable? And which one was the dependent variable? And almost always, the independent variable is going to go on the x-axis, like here. Now, the problem with math is that they always, when they give you a data table in math, isn't x always on the left of the data table? And let's say it's x and y. So you say to yourself, well, that's what the x must be on the left because that's the way they do it in math. That's not true. It's your experiment. Okay, so let me see if somebody can figure this one out. Which one of these variables is the independent variable? And why? Why did you say that? All right, raise your hand. Somebody take a chance. Yes?
The independent variable is mass because it's not affected by anything else. It's the one thing that is changing just because you changed it.
What do you think? Okay, now I gotta be careful. Wait a minute, gotta be careful. Because he had an idea and nobody else raised their hand, it's easy for a student to simply go like this. Yeah. All I'm asking you to say the reasoning he gave, you like that reasoning. Now, if you like that reasoning, and I ask you right now to repeat what he said, does that mean you could? You could. Yes.
think it's volume because it says in the above experiment, carefully measured volumes of liquid were taken to a balance and massed out. So it means that there was volume first before there was mass.
Oh, so,
Okay.
okay, so you read that. Now, but you know, that's good. Now, that's great. We just learned a little lesson, didn't we? Just because one person seems to be the only person in the class who thinks they know the answer, you still got to think about it, don't you? And thanks for reading. That was a good job. Now, I could have done this experiment, Alistair, either way. This experiment could have been done either way. And so I'll show you some of the clues. This is a big clue right here. In the above experiment, carefully measured volumes. That means, you know why that's 3.0? I made it 3.0. I made sure that it measured 3.0. And then I took it over to the balance and said, I don't know what I'm going to get, but I'm going to go ahead and put it on there. Okay, see what it is. Later, as we get back into doing these experiments, we'll talk about things like balance. You know, how do you weigh things on a balance? And of course, I would have this in a container, wouldn't I? And the electronic balance has a button. You can zero it to start out with, but then you can put the graduated cylinder on there by itself and zero it again. And it'll actually subtract that from all your readings. Then, if you put liquid in there in exactly 3.0 and put it back on the balance, this will be just the mass of the liquid. And that's a neat thing about the electronic balance. I didn't have that when I was your age, and we were constantly having to put it back on one of these balances. You know, you move little things over, and it would take like 10 minutes just to get one data point, whereas electronic balance, just like that. So anyway, another clue is, I'm not saying you couldn't have a coincidence where it was exactly 3.0, 6.0, you see that? But it looks like the human had something to do with causing those numbers to come out exact. Is that right? Now, when you're doing experiments, it doesn't matter. It doesn't have to do that. If you measure this carefully and take it to the balance and whatever you get, it really wouldn't have to end in 3.0, 6.0. You still can let it be any number you want, but the thing is, you chose it. Now, if you look down in this packet, you'll see down here where it says the horizontal axis. So when we do a graph, if we're going to do a graph here, the horizontal axis, that's this guy right here. Okay, that's called the x-axis in math class. I don't think math teachers use this word anymore. It used to be called the abscissas. You've never heard that word, right? We might as well get rid of that because nobody's using it anymore. Okay, so the horizontal axis is the x-axis, and in almost every case, that's where you're going to put your independent variable. And it's the one that you are manipulating. It's the one that you cause that number to occur. So when you create your own experiment in here, you say to yourself, well, I put this on there and I'm going to see what would happen. I put this much more on there and see what happened. You can almost see what the independent variable is. When you look at an ACT and you look at somebody's experiment, the first thing you want to do is figure out what's the independent variable and what's the dependent variable. And then you can almost picture, oh, I see what they did. They were changing this to see what would happen to this. You can already answer 2 or 3 questions just from that. Anyway, some other skills we'll get from this little packet from ACT. We'll talk about slopes and things like that. All right, so here, in this case, I would put volume on the x-axis. Now, it's time to grow up a little bit. I know what happens in middle school. They make a little box for you, and you put the word mass here. Maybe the teacher is good enough to say, put the label and then put the unit right there. Put the label, put the unit, okay? That's good. But then here's what I mean by grow up. You do not do this. You don't go gram, G, ML, and don't do that. Don't do that, period. You got that? No more. You're not going to do that anymore. I know this is mass, and I know your units are in grams. You get that? The body of the data table only has numbers. But I know some of you are going to be a hard habit to break because someone else wanted you to put G. I will. So I'm asking you not to do that anymore. I've never seen a scientific data table like that, and you don't need to do it. Now, also reminds you to put the label and the unit so you yourself know what's going on. All right, so that's pretty easy. This must be the dependent variable. Now, you guys are not in you got, wait a minute, I can't even think you're dependent. You're not in stats, and so they actually use a couple of different words. They said they call this, what is it? Oh, okay, what do they, in stats class, what do they call the independent variable? Experimental or explanatory? Okay, they told me, I never use that word, but I think in stats they call it the explanatory variable, and you don't call it dependent, you call it the responding. And I like that word because you know why that came out to be 2.1? Because that number depended on what I chose here, isn't it? I chose these independent of anything else. Nobody made me say 3. I just chose it, didn't I? But guess what? You won't get 2.1 if I don't pick 3 here, do you? This number does depend, or like Sarah would say, this variable does respond to what happened when you chose that. So this is you. You're manipulating this variable. And I would be a little careful about this. I would 3, 6, 9, I'd be a little careful. A lot of it, your pre-made labs do it all the time. They'll go 5, 10, 15, 20, 25. I understand that. You can do it, but you know what the human mind does? We have this thing, you have bias. And so what happens is if you start picking 5, 10, 15, 20, you'll say, oh, I see the pattern. When I say 5, oh, look, when I get 10. And then what happens is you're supposed to get this other number in your head. And then you start measuring, and guess what happens? You get pretty close to it. Oh, yeah. And so you kind of think ahead of time. You said, I think I know the pattern. And it happens every year. I've seen people do it. They think they know the pattern between 1 and 2 and 3. And then they start thinking, I know what 4 is going to be. And it actually makes their measurement bias. They actually measure something a little differently than they would. Okay, let's go on down now. And by the way, this experiment could have been done either way. I could have, on the balance, put in a certain amount of liquid until it was exactly 5 grams. And then I could read the graduated cylinder to see what the volume was. See that? I could do this either way. But that's not what I'm going to teach you. There is a reason. There is a reason why this person wanted this to be the independent variable. You get that? They never say that in math, do they? There's a reason why that's X. They never say that. But in science, there's a reason why I'm doing this experiment this way. Let's go on down now. Besides putting a label, you always put units. So we're going to go like that. We're going to do a graph here. You're going to do that one at home. And so now we have things set up properly. The vertical axis, and I remember a long time ago, some teacher taught this is like yo-yos. Yo-yos go up and down. That's the y-axis. But I think you've probably done enough graphs in your life to know the x and y axis. Is that right? Okay. This is called the horizontal axis. This is called the vertical axis. You got that? Okay. All right. Label and place units on each axis. Do not overcrowd with too many numbers. And then we're going to plot the points. And so what we're going to do here, I'm going to get you started. You'll go in the back here. And what we're going to do is I have plenty of room here for my labels and numbers. Plenty of room here, okay? Now, what I'd like to do is, what goes on the x-axis again? Okay, let's do that. I have to make sure I have room for my numbers. So I have the label and I have the units. And what goes on the x-axis? Is that right? Okay. Now, here's, I consider this to be the most tedious or the hardest part of graphing. You guys will eventually, I will have you do hand-drawn graphs. I'll teach you the theory of scientific graphs, but eventually I will let you have we have a computer program, and you will be doing this on a computer. And it'll actually ask, what's your independent variable? Well, you have to know, don't you? What units you're going to have. See that? So eventually I'll let the computer do the work for you, but you're going to be doing hand-drawn graphs to begin with. So the most tedious part for you is scaling the axis. See that? So what I want to do is, and I know this is just me, but I consider if you use less than half of a graph, I'll take off points because I want to spread those numbers out as much as I can to get as much detail as I can. So how do I go over here, and what is the highest number I need to go to for volume? 19. Now, so we go down here, and let's just do a quick count. And somebody said it was 25 by 45, so this must be the 45, right? Is that what this says over here? It says 25 by 45. Okay, so let's see. What if we went by ones? Let's call that 0 and say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so if we went by ones, 5, 10, 15, I'd be done right here because my highest volume is there, and that's not good, okay? So we can't go by ones because it would we'd be wasting all this graph, wouldn't we? What do you want to go by?
Twos.
Okay, let's go by twos. Then I go 2, 4, 6, 8, 10. Now I'm done here. Oh, it's just the opposite. Okay, you got to go by halves. Okay, so let's try it. Ready? Here's a half and here's 1. Here's 1.5. Here's 2. Now I should have used pencil. Here's 3. Here's 4. Here's 5. 6. 7. 8. 9. And I'll put a big mark there. So this is going to be my 10 here, okay? Now, 1, 2, 3, 4, 5. I do not want to see you labeling every line, okay? It makes it look crowded. There's no reason for it. If I say 5 and I says 10, can you find 6? Yes. We're not going to write 6, 7, 8. We're not going to do that, okay? So go skip 1, 11, skip 1, 12, skip 1, 13, skip 1, 14, skip 1, 15. Okay, go ahead and mark these out. 16, 17, 18, 19, 20. That worked pretty well, didn't it? Does everybody see what we're doing? Again, this is probably the most tedious part of graphing, is scaling. Now, here's another thing. Here's a habit we have to get out of. Yes, when I was in math class, how many times did I do this in math class? Woo, woo. 1, dun, 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 dun. You ever do that? How many times did you make your own little graphs? See that? Well, in math class, they always said if there's 1, 2, 3, 1, 2, 3. And so you're in this habit of thinking that however I scale the x-axis, I have to scale the y-axis the same way. That's not true. Everybody get that? You can scale each axis by itself independently. So now let's take a look at mass. What's the biggest number we have to get for mass? And it goes all the way to 16, doesn't it? So in my mind, that's close to like 20. So what am I going to go by? There happen to be 25 numbers here. I pre-counted those. There's 25 here. What are you going to go by? Ones? Let's try it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 10. 1, 2, 3, 4, 15. 1, 2, 3, 4, 20. Okay, now did I use at least half of the axis there? So I'm going by ones here, I'm going by halves here. Everybody got that? So that's another thing I want to teach you. You don't have to use the same scale. All right, almost ready? So if I were to test you, I would have an experiment. I would show you experiments somebody did, and I would show you their data table. And I would expect you, by reading their experiment, to say, oh, I know what the independent variable was. I'm going to put that down here. I'm going to scale the axis. I know what the dependent variable was. I'm going to scale the axis. Now we're ready to go. Ready? Now here's where we're doing something a little different than math class. The first data point, and remember, is we put x first and then y. Isn't that right? Well, remember, this is going to be your x because that's your independent variable. So we need 3, 2.1. 3, 2.1. 3, 2.1. Now, what I want you to do is you put a little dot, but then you put it's called a point protector. So you put a little dot, because if I start putting big fat dots, that's going to give me more error. So I want a little dot with a little circle. Now, the reason I put a circle around it, and when you do a computer program, it'll say, do you want point protectors? You say yes, because when I draw my best fit line, if I have a little dot and a line goes right over the top of it, I won't even know there's a data point there. I need to know where my data points are, okay? So this is called a little dot with a little circle. The little circle is called a point protector. That's the lingo they use in the computer. All right, let's go ahead and continue plotting the points. Okay, continue plotting the points. Next one, 6, 4.5. By the way, take your time on this. There's no reason to do the whole experiment and mess your graph up. What did I say? 6 and 4.5. 6, 1, 2, 3, 4, 4.5. Little dot, little circle. Okay, a little bit different than math, right? A little bit different, not a lot. Next one is 11, 9.3. 11, 9.3. 9.3, a little dot, little circle. The next one is 15 and 12.1. 15, 12.1. Just take your time. There's no no hurry. And then 17 and 14.2. Okay, and the last one for me is 19 and 16. 19, 16. All right, what do you think? I have a couple more minutes here. Now, what I'm going to do is, so far, things are sort of like math, right? A little bit. We scale our axes differently. We decided which one was the independent. When you guys do experiment, I'm not going to tell you. You're supposed to know which one's the independent variable. And then the next thing I do is, this is the hard part. Do I think that there is some kind of a mathematical relationship between these two variables? And I think there is. And what do you call it? I know you guys know it, but what do you call it if the relationship seems to look like a straight line relationship? What is it? Linear. Now, we know that it's a linear relationship at this point. That's all we know. And then what we're going to do is we want to draw this line. Now, in order to draw the line, in middle school, they would go, you would automatically go at 0, 0. And that's another question that you have to ask in your experiment. Am I allowed, do I have to make this graph go through 0, 0? Everybody think that? Do I have to do that? And the answer is not, no, not really. Even though you may have zeroed out everything, like on the balance, I zeroed out the balance. I had one year where somebody was doing an experiment with pennies, and they didn't understand why their graph, they were really careful, and their graph did not go through 0, 0, and they were trying to make it go through 0, 0, but the graph shouldn't have gone through 0, 0. And they said, I zeroed everything. I zeroed the balance. I zeroed the graduated cylinder. They say, how do you do that? I made sure there was no water in it. I looked at the graduated cylinder, and they had a penny was stuck in the bottom of the graduated cylinder. They never saw it. And so every time they were reading something, even the mass, it was different because they thought they had zeroed out, but they didn't. So many times in science, when something doesn't go through 0, 0, it tells them something. There's something the way I designed this experiment which is a flaw. Now, it may be something I can't zero out, or it's something I need to zero it out. You get that? If I said, let's zero out all the noise in this room, I wouldn't be able to do it, would I? Hey, let's do an experiment in the dark. Even if I turn off the lights, I'm going to have some background light, aren't I? It's going to be some light in here. I might not be it. We're going to do one later with pendulums. And a pendulum should be in a vacuum. Well, that's not going to happen. So sometimes we can't zero something out. And I know it's not going to go through 0, 0. All right, here's what I'd like you to do. I guess for right now, I'd like you not to draw the line, and we'll start from there tomorrow, okay? All right, thank you very much.